Hello everybody, and in this video we're going to be learning about stars. Now, our sun is the closest star, and its gravity keeps the planets, asteroids, and comets and everything else in orbit around us. Our sun, though, is a medium-sized star, and it's a yellow star. It's only about 4.6 billion years old, which seems really old, but is it? Now, our sun is only one of billions of stars in the Milky Way, which is the galaxy that we're found in. In this galaxy, the Milky Way is 100,000 light years across. And our sun is actually revolving around the center of the galaxy in one of these pinwheel arms. And it takes about 200 million years to go around once. Now, a star is an extremely hot ball of gas and plasma held together by its own gravity. Our sun is the same way. It's gravity that holds everything and squishes it together. Now, how does this make stars work? Now, the stars are born in nebula, these stellar clouds, and the gravity pulls gases together, mainly hydrogen. When that hydrogen gets close enough and energetic enough, it will fuse into helium. And that is a process called nuclear fusion. And at the center of every star, there is nuclear fusion occurring. Now, when fusion occurs, energy is released as heat and light. And that gravity that's pulling in is counterbalanced by that heat and energy trying to leave. And this is what determines what happens to a star, whether it's a small or medium star or it's a large star. So the life of the star is determined by its mass. All that stuff that it contains, the more mass it has, the more massive it is. And this will change its life cycle. We can see that life cycle here. That life cycle starts off with that planetary nebula, and it can go through several stages, right? If it's a small enough star, like our sun, then it'll form a red giant and then a planetary nebula, and then into a white dwarf. But if it's massive, it'll become a red supergiant, supernova, and then become a neutron star or a black hole. Now in this picture, we can see our size of our sun, which is right here. And this is a medium-sized sun, but they can get much, much bigger than that. So these are smaller, medium-sized stars like our sun. Now for their life cycle, they start off, they expand, and then those outer gas layers create that red giant. It gets very big as the core begins to collapse and burn brightly as a white dwarf, and it kind of spits off that outer layer. Eventually, that white dwarf will burn out completely into a black dwarf. Now, if it's a very large star, we can see in this picture, we can get much, much bigger. And it is unbelievably big. It's so hard to grasp how big this is. We can see in this picture that our sun here would be a tiny little dot here as we get into Arcturus and Aldebaran. But as we get even bigger to stars like Antares and Betelgeuse, even those are smaller than some of these large stars. So stars can get extremely big with a lot of mass. Now, when the hydrogen fuel runs out, they can continue to fuse larger atoms until gravity finally causes the core to collapse. And the outer gases will expand out to create a super red giant. And the core becomes very dense, so dense that all that other gases spill out into a supernova, and we get either a neutron star or we can also get a black hole. Now, black holes uh, have an infinite density. And here it says on the slide the size of an atom. Well, we don't quite know. We expect it to be at least that smaller. Um, Scientists tend not to like to use the word infinity, but that's what the calculations look like. And this is actually the first picture of a black hole. You can see the event horizon where the light can escape. We have an accretion disk around the outside, kind of looks like a astronomical donut. This picture was taken in 2019. And this is in the center of the Messier A7 galaxy. And that dark circle, that black hole itself, is 25 billion miles across. Now, if you went into a black hole, which I wouldn't advise, you go under the process of spaghettification, which is where your body is strung out atom by atom. And you would cease to be, but this process, when you get the event horizon, you kind of get stuck there. But this is just all theoretical. We don't really know what exactly will happen. Now, remember, this is all based on the size of that star and what happens. And you're only going to get that black hole with some of the most massive stars possible. Now, we say the sun is a yellow star. What does that color tell us? Well, each of these stars has colors that tell us the temperature that the star is at. And it's also somewhat an indication of the size. So we're going to go through a bunch of stars and kind of look at these differences. Now, a blue star would be very hot and fragile or Spica like this. And if we look at the constellation Orion, in that bottom right is Rigel. And Spica is in Virgo in that constellation. Looking at a white star, that's a little bit cooler. The stars Vega and Sirius are those. And we can see Sirius just at the bottom left of Orion the Hunter, and Vega is way up in the Lyre the Harp. The yellow-white color, still cooler yet. Procyon is in Canis Minor. We can see here, right next to Orion, we have Procyon there. See a yellow-white star, and our yellow star, well, guess what? That's our sun. That's the best example we have for that yellow star. Orange Arcturus. Remember, Arcturus is a very large star. We have here in the bottom of this picture. And finally, we can get red stars. These red ones like Betelgeuse and Antares. Surface temperature coolest. And Betelgeuse you can see in the top left of Orion, and Antares is in the constellation Scorpius. Now, the hotter the star, the more quickly it burns through its fuel. Remember, there's only so much hydrogen and other elements that just keep getting fused together, and that's the nuclear fuel. And the cooler stars will burn through that fuel more slowly and therefore last longer. Some red dwarfs, which are the coolest and smallest stars, will be around for trillions of years. Now, yellow stars like our sun, they're medium temperature and size, and they will last for billions of years. Blue giants, though, are very big and very hot, and they will burn through their fuel in only a few million years. There's a picture of one here. And these blue supergiants are huge and extremely hot, and it only takes tens of thousands of years to burn through their fuel. And that's just a very big star, too. Now, here's a great picture of hundreds of thousands of stars. There are so many of them, and it's really awesome to learn more about them. So thanks for watching this video and learning more about stars.